I do good for good's sake, with no thought of compensation. And as I've evolved to the point where I don't care a thing about getting rewards. I'm not an atheist, but I behave as an atheist. I do good for good's sake, with no thought of compensation. And as I've evolved to the point where I don't care a thing about getting rewards.
喂，这上面的那个怎么没了？Hey guys, today we will share the how to build Zuul by using Operator framework. And I'm Neil, and this is my colleague Zhou Xiao. We're from EasyStack Research and Develop team. So first, we're gonna talking about the Operator framework. There are two main paths in the Operator framework. One is Operator-SDK, and another is Operator Lifecycle Manager. So the Operator-SDK helps you to generate your operator code easily. You can build your Zuul operator code by using Operator-SDK in the Operator framework. And another Operator Lifecycle Manager helps you to control the whole lifecycle of the operator. And the operator code you build will be pushed to the operator catalog, and you can create subscriptions resources in the Operator Lifecycle Manager namespace, and it will subscribe the latest version of the operator in the operator catalog. And the operator will be deployed in your cluster. And then you can create the Zuul by Zuul-Operator, and the Zuul-Operator will control the application lifecycle. Yeah. Okay. And let's see why we should make Zuul to the operator. There are 4 reasons. The first is that Operator Lifecycle Manager controls the whole lifecycle of the Zuul operator, and the Zuul operator controls the whole lifecycle of the Zuul. Zuul upgrade and scaling or scale out will be easily. Another reason is Zuul can be defined as Kubernetes resources, and sharing the same control plane with Kubernetes. You can imagine that you can interact the Kubernetes API to achieve Zuul scaling or scale out or downgrade, upgrade easily. So that's the best reason why we make Zuul to the operator. The third reason is that Zuul operator can downgrade and upgrade easily by using Operator Lifecycle Manager operator, OLM operator, to create catalog subscription and install plan. If you set the install plan, the policy to automatic, it will automatic upgrade your Zuul operator to the latest version. You don't worry about the upgrade or downgrade of the operator. The last reason is that Operator-SDK helps to generate Zuul-Operator framework code, so you can write the operator code easily. So let's see how to make it. This is my colleague Zhou Xiao. He will introduce the Zuul-Operator code here.
好，谢谢我的同事孙斌。然后既然他用英语的话，那我就用中文，简单的花个1分钟，大概就过一下。就是对于这个 root operator 的话，其实从代码上来说，大概我们只要简单的从 API 层和它的 controller 层定一下就可以。在 API 层的话，其实我们大概就需要定一下这个 root operator， 我们需要它展示什么，以及我们从它的 root 的这个 CICD 资源中去控制什么。打个比方，在上面其实我们需要控制的 root version 以及 root schedule 的它的副本数以及 Garrett 的信息，其实我们在 API 层只需要做这样的设计就可以了。然后其实对于 controller 层的话，其实这是一个就是很基本的就是控制逻辑嘛。对于我们如果想要去控制这个 root version 的话，其实最简单的方法，我们只需要提取这个 root 下面的root schedule 的这个 deployment 的 image 的version， 然后把它比对一下。如果是不同的话，我们就用 K8s 的 client 把它给 update 进去，让它去做自动的deployment 的update， 这样我们就可以实现对它 version 的 control 了。如果大家以后对这个有兴趣的话，等这个项目就是 stable 之后，我们会把它推到社区里面去，大家可以去关注一下入这个社区。好，接下来我们就剩余一些时间可以 demo 一下。
Okay, thanks for Zhou Xiao. And if you are interested in the project, we will push it to the GitHub when the meet end. Okay. So the second part is using Operator Lifecycle Manager to control the whole life cycle of Zuul-Operator. There's a simple diamond here. So let's do it. And this is a single Kubernetes cluster with Operator Lifecycle Manager. You can see 2 ports in the OLM namespace. They are catalog operator and OLM operator. The catalog operator controls the life cycle of the catalog, and the OLM operator controls the life cycle of OLM. So let's create the subscription to subscribe the operator package. You can see the YAML of the Zuul package subscription. The channel defines which channel you subscribe to. I set it to alpha, and it will download the alpha package, operator package, to the cluster. Okay, you can use kube control get csv-n OLM to get the latest CSV. The CSV is the operator definition. You can see the latest version is version 0.0.2. Okay. And the Zuul-Operator controller has been running. Then we create a Zuul here. The Zuul YAML defines the Zuul information here, includes the Garrett address and the schedule size. We just set it to one size to demo it. Okay, you can see the Zuul scheduler, Zuul merger, Zuul web, and Zuul executor has been running. Then we create an ingress of the Zuul web to visit the web. Okay, you can see the Zuul web has been achieved. So let's put a code recheck here and see the effect. Comments recheck. Okay, you can see the patch has been running the CI check. And cause I don't have enough resources to run the actually CI, so the dam is in here. In the end, we will talk something to the write more controllers to support more sense here. The operator we write just support to generate a Zuul cluster, and you can see the size of the cluster, but it does not support to back up Zuul keys or restore Zuul keys or another fraction. We will support in the future. If you are interested in the project, we will push it to the GitHub and you will see it. Thank you.
Okay. That's okay. That's okay. I don't need. Okay. Hello, everyone. My name is Balázs Gibizar. I'm here to talk about a small tool that visualize placement resource view. As you most probably know, OpenStack started collecting the resource view in a separate service called placement, and today it's already tracking CPU memory and disk utilization of the compute hosts. But in the recent releases, we added a lot of other resources and other features to placement, like tracking bandwidth, tracking cyborg accelerators. And through this, we added a lot of complexity into the resource view of what is stored in placement. When you want to query the placement resource view, you will end up using OpenStack CLI, because there are resource provider subcommands in the OpenStack CLI to get that. You have to go and list of the resource providers, check the inventories, check the trades, check the aggregates, and also you have to know what are the consumptions in placement. So you have to know what is the consumer. Consumer tend to be a Nova server, so you list the servers, remember the UIDs, and go back to placement and query the allocations of the servers. So this is a lot of command to remember, and the output of these commands are referring to UIDs. You have to correlate between command outputs. So when I use these, I always end up drawing a picture by hand. And then I realized that, okay, that picture can be drawn by a tool, not just by me on a paper. So I ended up implementing something that visualized the placement information. And that's ended to be a OpenStack CLI plugin. You can pip install it, called OSC Placement 3. It actually provides two new OpenStack CLI subcommand called resource provider tree list and resource provider tree show. The tree list will give you the whole resource view of the overall cluster, and the provider tree show can be limit this output to a single provider tree, which is basically a compute node. And this tool emits graphviz.formatted text output that you can pipe into whatever tool that understands graphviz, and you will get a picture. How this picture looks like. So this is an output from a 2-compute node dev stack, which has bandwidth configured on both compute nodes, and one of the compute nodes has even one FPGA from Cyborg. So this is a pretty complex picture already. Let's zoom in. This is one compute node from this 2 compute nodes placement, two compute nodes dev stack. All the boxes are resource providers. The top box is the compute resource provider, and down below there are child providers, because we have to have more fine-grained control about who reports what kind of resources. If you zoom even further, then this is the compute root provider. This provides inventories from different resource classes like disk, memory, and vCPU, and the output contains the used and total and reserved amounts of these resources. This also shows the traits the compute has. These are compute capabilities. And it would show aggregates if there would be any aggregate defined. I don't have those. And of course, it shows the name of the compute and the UID of the resource provider. And on this picture, which is more interesting, is there are arrows that shows relationship between providers and consumers. So the normal arrows are parent-child relationship between the root provider and the child providers, and the dashed arrows will be consumptions. If you go down on this picture, this is a grandchild provider actually for the compute node that provides the bandwidth. But what is more interesting is the bottom of the picture that is a consumer. In this case, this is a server booted by Nova. And there is 2 arrows coming out of this that presents 2 types of consumption by this consumer. The one is in the left side going to the grandchild bandwidth provider. On the right side, this arrow goes up to the root, and both arrows are annotated with the amount of resources this consumer consumes from that specific provider. So this is the structure. Okay, what's good for? Why I did this? I had to troubleshoot a lot of resource allocation problems in my environment, and as I said, I always ended up drawing pictures, and I wanted to automate that. Also, it helped me to understand how placement models resources, how placement models consumption. And last but not least, as a Nova developer, I had to understand how we test the complex placement interactions. And we have functional tests both in Nova and placement that sets up pretty complex scenarios. And those test cases tend to describe what they are doing. But I wanted to verify that the description is correct. This is what the fixtures tells me what we'll do. It's actually what it does in placement. So what I did, I just ran this tool against the database created by the test case and then compared the description in the test case with the actual picture I got from the tool. What is it not good for? If you try to run this against a big deployment, especially the OpenStack resource provider tree list command, then it might fail on the client side because this goes and queries everything out of placement. And today, placement doesn't have one bulk get API, so I have to iterate through a lot of API calls and then gather all the information in memory in the client side and then generate the graph. So actually, I tried this against 100 compute node deployment, and it takes 20 seconds in my laptop to generate the picture. That's still okay, but I wouldn't run it against 1,000 nodes deployment. That most probably blow your client. What you can do is you can use the tree show command because that's limit the output to a single compute by the name of the compute. So that's always safe to run because it's just one compute. That couldn't be that big. So do you miss something? If you miss something, tell me. I'm Gibby on Freenode, and I am here around this summit and PTG. And of course, you can go and fork the repo and send me pull requests. It's not under the governance of the foundation right now because it's just Chris Dent and me who is contributing to that. So it was easier just to keep it as a GitHub repo. But if there is enough interest, I can move it under the foundation stuff. I already know some of the things that missing. For example, placement aggregates today is just UIDs in the picture, but I can draw arrows to represent it visually. Also, there are relationships between consumers. If you resize or migrate a server, then that will mean that you will have two separate allocations, one on the source host and one on the destination host for that server. And that would be just two separate boxes on this picture. I should correlate them as well, that these two consumption because of the same server being migrated at the moment. And also, as I said, I use a lot this in the functional test of Nova and placement. Today, I have patch proposed to placement to enable dumping this resource view as a .dot file at every functional test step in a placement functional test run. So you can actually step through the evolution of this picture as the test progresses. You can enable it with an environmental flag. And also I have a snippet of code that you can copy into the Nova functional test, and then you can get the same. I also plan to propose that patch against Nova to automate this. But if you have anything else, then please tell me. Thank you.
Okay. Next one, next one. Yeah. That's right. That's the one. Right. Yeah. Yeah. Sounds good. Okay. Okay. All set? Okay. Cool. Hello, everybody. We'll be talking about networking acceleration today and how we can enable that with the Cyborg service in OpenStack. Okay. Okay. So we'll talk about why we need hardware acceleration in the first place. We'll talk about some usage models for how we can use networking, etc. We'll talk about where Cyborg is today. We don't have networking support yet. We'll talk about how to enable networking support in Cyborg. And 10 minutes is pretty much all we can do. Okay? We had a more detailed discussion of Cyborg and a project update. We can talk about that also later. Okay. So why do we need to accelerate networking at all, right? So if you look at where we are with OVS switching or other forms of network switching, they consume a lot of CPU. So especially as you move towards 100 gigabits per second, the packets rate go up. So there's an increasing need to offload them to some kind of a hardware accelerator. That's also needed for improving latency and jitter, etc. And this is one primary reason. As we move towards 5G, it's another important trend. We are seeing there's a strict requirement for latency and jitter needs. And we are kind of not there yet with software-only implementations. And furthermore, the 5G standards are also evolving. It's not some fixed thing. So we not only need accelerators, we want them to be programmable. So it's important to have not just some kind of ASIC accelerator, the ASSP, but something which can be programmed repeatedly as the standards evolve. And the third motivation is edge computing. This actually adds on to the previous two. As we enable new applications like augmented and virtual reality, they have stringent latency needs of their own, and that's going to complicate things further for other needs. So we want accelerators that are programmable and also which are deployed either in the edge or the data center, possibly a combination of both. So these are the reasons which are driving us towards that. So within OpenStack, as you may know, we've got a Cyborg project for enable accelerators. And what it essentially aims at is lifecycle management for all accelerators. It's not only for GPUs or SmartNICs or FPGAs, any one of them, but all of them. We already have support for many of these types. We don't have networking support yet, but we are increasingly hearing from various partners and customers. We should be supporting some form of SmartNICs and programmable accelerators and so on. Okay? So there's a quick overview of Cyborg. It's only 10 minutes. I won't spend too much time on this. But basically, Cyborg is a service. It's vendor neutral, like pretty much any other service. It's also supposed to be hypervisor neutral. The way it works is that we've got an API server in the controller, along with Nova, Neutron, and everybody else. And we also have our own database and a conductor. So it looks like a regular project in that sense. We also have an agent running on every compute node. And that agent has a bunch of libraries which we call the drivers. The drivers in this context are basically libraries which the agent can load and which are device specific. So for example, we've got a Cyborg driver for NVIDIA GPUs, we've got a Cyborg driver for Intel FPGAs and so on. Okay? So plus for FPGAs, we'll also use the glance storage for storing the bit streams along with the VM images. Okay? Please stop me if you have any questions. Okay. So why do we need Cyborg in the first place? If you're looking at GPUs today, we typically use them with PCI whitelists, and they're typically difficult to use. Basically, it's a configuration file which you need to keep updating. We had a forum this morning where we had several operators present. They also pretty much concurred that it's a difficult thing to use. But when it comes to programmable devices, it won't even work anymore because You could have a FPGA with a certain PCID with, let's say, gzip inside it. Another FPGA with something else like a vRAN workload inside it. So looking at the PCID does not tell you what's inside it. So you can't ask for a VM with a gzip offload or a VM with a vRAN offload. You have to necessarily go by PCID. So with programmable components, you can't even use PCIDs anymore. CyBorg solves those problems by doing two things. You don't need a config file. You don't need host aggregates. You're going to use the drivers to discover the devices and populate them in placement automatically. So Nova can query it and get everything in a holistic fashion. Plus, we also find the things inside the drivers. The CyBorg drivers can find out what kind of function is implemented, what bit stream is programmed, and so on. So all the information is available to enable use cases like, I want an accelerator with vRAN offload. We can make requests like that. Okay? So the key idea here is that we're going to leverage placement, right? So we're going to create resource providers in placement for every accelerator type. There's a smart NIC or a GPU or FPGA, we'll create a resource provider for that. And the device properties will become traits in placement. So we've got a whole thing worked out. So the way you would use that today is that you would configure the drivers. So if you got an NVIDIA GPU, for example, you put the GPU driver. If you got a smart NIC, you'll put the corresponding driver in the future, etc. Then you load up any bit streams you may have for FPGAs. Then you define something called a device profile. So normally in Nova, you've got a notion of a flavor, right? In the flavor, you define extra specs for additional resources. We just took the same concept and factored them out. Because if we put everything in flavors, the number of flavors will explode. We don't want a flavor explosion. Typically, operators do use flavors for billing and accounting. So we don't want too many flavors lying about. So we put them in a separate thing called a device profile. There's an example of a device profile in the bottom. So essentially, it looks like extra specs. You've got notion of resources and traits, except that instead of plain key value pairs, made into kind of a JSON format. It's kind of easier to manipulate. Okay? So you do all that stuff, and finally, you can just create a VM with a particular flavor. And we got a whole workflow worked out with Nova for how we can launch a VM with this flow. Okay? So this is what we have today. And the question then becomes like, how are we going to adapt this for networking? To understand that, we first need to understand how it works today without networking. So the very broad idea is that when the Nova sees a device profile name in the flavor, it's going to query CyBorg first and say, give me your device profile information. So it gets the resources and traits requirements from CyBorg and merges them with other request groups from the flavor and other sources. It makes a consolidated list and then queries placement with that. So when placement returns the values, it returns not only the compute host, but also the devices. It's going to say, here's a compute node as a resource provider, and the device is a nested resource provider. So essentially, it's returning a tree of candidates. So basically, the various candidates are available to Nova. And the Nova scheduler is going to pick one of those. When it picks one, it's essentially picking a host and a device. In contrast to today's flow, there's only a host involved, right? So once it does that, it's going to call back into CyBorg. For those of you familiar with Neutron, we got a notion of port binding. So we have a similar idea here in CyBorg called accelerator request binding. So essentially, you choose an accelerator request and say, bind this to this host and this device. So once you do a selection, call to CyBorg for binding. And binding, in this case, asynchronous, because it may involve potentially preparing the device or reprogramming it. So Nova is not going to block on that. It's going to issue the bind request and move on. It's going to call into Neutron and Cinder and everything else. And while that's going on, it's also sending a message to the word driver. The word driver will finally query CyBorg to get all the details. So the broad idea is that instead of getting the PCI devices from a whitelist, we're going to get the PCI device from CyBorg after the device is prepared. That's the overall idea. And this is what we're currently implemented. We already have this in train. It's been implemented on the CyBorg side. On the Nova side, we've got a bunch of patches. They are still being reviewed, so it's not fully merged. But this is what's been implemented on the CyBorg already. The question now is, where do we go forward? Right? First, we need to complete the Nova integration. And we already have many basic VM operations working with the accelerators today. That includes creation and deletion of VMs. You can pause, unpause, stop, start, resume, all of those things. But we don't have networking today. So how do we get networking? So here's the meat of the idea, right? This is more like a proposal. We are kind of working on some ideas right now. It's not yet proposed in the community yet. But basic idea is, instead of setting a device profile name and the flavor, what if I set a neutron port instead, right? So you may want to create a VM with one management port and let's say one offload port. The management port stays the same. You don't need anything new for that. There's no offload there. So you do it the old-fashioned way. But for the one which requires offload, you put this device profile which says, I want this trait on this kind of device. So if you put that in the Neutron port, Nova should be able to query Neutron, get those device profiles, combine them with other request groups, and do the placement query as before. So when it's choosing a candidate, it's actually taking the Neutron needs into account. Neutron today does not influence scheduling, but with this process, we are hoping that it can influence this Nova scheduler itself. Okay? So we do that. So net result is like the old way that instead of getting a PCI BDS whitelist, we're getting it from Cyborg. Cyborg would have taken into account what Nova requested in the binding process, right? Once the Cyborg binding completes, you get the PCI BDFs, and you pass that to Neutron for binding. So Neutron ports today get the PCI BDFs in the whitelist. Instead, you get them from Cyborg and then pass them to Neutron. So from Neutron's point of view, it's very little change. In fact, the only thing we're proposing is that in the port binding, there should be a device profile name as a key value pair. It's the only change you need in Neutron. At least, sorry? We are proposing in the U cycle. Whenever it gets merged, it gets merged. It's very difficult to foresee when it's going to get merged. But we want to propose this as a patch in the new cycle. Yep. Yeah. Absolutely, yes. So we propose to submit a specification and associated patches. We'll also talk to you guys in the course of this PTG. Yeah, cool. Okay. Yeah, cool. So yeah, that's the basic, yeah. Sorry, can you please use the mic? The question was, can you get rid of the Nova compute?
Have a Cyborg agent and drivers without OpenStack in play. So
can we use a Cyborg agent and drivers without? Okay.
Suppose now today I have a bare metal. So
okay.
On top of that, like I would be having my DPDK drivers and then doing my abstraction with the DPDK for the underlying NICs. Right.
Yeah.
So and my DPDK provides me the flexibility to whitelist the NICs and move it to the fast data path. Usually.
Okay.
So can I inflict a Cyborg agent and drivers there? Like I not even have my OpenStack agents coming into play. Probably.
Are you talking of DPDK inside a VM or DPDK in the host?
DPDK on a host.
On a host, okay. Yeah, it's a slightly different use case, yes. Right now, I've been focusing mostly on VM level offloads.
Okay.
I think what you're thinking about is something like OVS offload or offload from the host.
Right. Even if that is the case, can I spawn my VM on a bare metal using libvirt, and I have my can I have my Cyborg agents there, right? Or
yes.
It is heavily dependent on Nova compute as of today.
The fundamental operation of Cyborg in terms of programming, by itself, the discovery and programming are almost standalone.
Okay.
So it should be possible to list your inventory, do programming, etc., without Nova being involved. The reason why we're involving Nova is to put up VMs.
Okay.
So the act of spawning a VM through word driver, scheduling, everything is in Nova today.
So say suppose I have an alternate in fact Nova which spawns my VM. So my Cyborg can still be used there.
Yes, in principle, yes, we need to have the right way to call into Cyborg to do all the preparation. If it's like API compatible with the way Nova works today, it should work. Yeah, right.
Thank you.
So you are suggesting API compatibility for taking off Nova compute from there?
API compatibility for the way you call into Cyborg. Okay. Cyborg already defines some APIs in a standard way. Nova simply calls into them. The standard REST API is documented.
Correct.
It's version 2 API which is published in Train.
So
if you just call into them, it should work.
So subsequent question to that is, OpenStack controller is there, right, in the
Yeah.
left side.
Yeah.
I don't need Glance, Neutron, Keystone. If I put a Kubernetes controller, how does it work?
Oh, I see. Okay. That's a little different question because Cyborg API controller, the server, is actually running on the OpenStack controller.
Oh, I see.
Right. It's part of the REST API server.
So you don't have standalone version right now?
That is correct.
Okay.
Yeah, it's tied into the OpenStack infrastructure. Yeah.
Thank you.
Right. Okay.
I think it'd be a great idea if we gave you a full example of what's really going to take place tonight when Jasper Philharmonic unveils itself to the stage Carnegie Hall audience.